that, get that. And okay. Here we are. All right, so I started 1.5. I'll do more of 1.5. Again, cross off 17 and 19 if you didn't already do so. Okay. I think I can come close to finishing everything today, but if not, I still have tomorrow. Okay, so schedule-wise, I'm aiming to finish everything. So here we are, September the 1st. So happy September, everybody. We're no more August. We're into September. So again, buffer day doesn't mean holiday. It means I'll take questions for the entire time. But if you don't ask me any questions, I'll just get started with chapter 2. Okay. Who knows? Maybe I can sneak in some of chapter 2, 2.1 even tomorrow, since I'm close to being finished with 1.5. I don't think I'll quite finish, but I can probably finish early tomorrow. Okay. Monday's a holiday. No school at all. So not just my class. Any classes at CSM. Monday's a holiday for Labor Day. So we meet again on Tuesday, the 8th, it looks like. Okay. All right, so I did a bunch from here. I'll do a bunch more. Again, for the exam, I tend to give about 10 questions. So if there's 1, 2, 3, 4, 5 sections, then expect 2 questions for each section, I guess is a reasonable assumption. Is that right? Okay. I don't make them all the hardest. I don't make them all the easiest. So expect 1 or 2 easier type, 1 or 2 harder type, but the rest are kind of in the middle. Okay, just so I can distinguish A, B, C, D, and F students. But again, I'm not really out to get you, so to speak. The average student should be able to get at least a C from me. Okay. Yeah, did somebody want to say something, or no? I am hearing some background. So again, everybody, please mute yourselves unless there's something that you really need to say. So please check that you've got yourself muted. Okay, and yeah, there's a lot of redundancy by design to make sure that everybody gets it. So I'm going to, since we're recording, I'll show you all the problems again. So on page 66, there is that, and that, and then on page 67 looks like there's that. And that, and that. And the next page, 68, and that, and that, and that. Okay, so that should have it. So when the video comes out, just, move forward or backward as necessary. All right, so I'm going to jump to problem 38, where it said e to the negative ln of 2, e to the negative ln 2. Now, we said whenever you have an e and an ln next to each other, they cancel each other out. But there's a negative 1 that's in the way. Okay, so how do I get rid of that negative 1? The trick is take that negative 1 and bring it up as an exponent. Recall one of the properties of logs. Okay, one of the properties of logs is that if you have a coefficient in front of ln, you're allowed to bring it up as an exponent. So negative ln 2 is the same as negative 1 ln 2. And you just make that negative 1 climb up here. So it looks like e to the ln 2 to the negative 1. Okay, so again, the original was e to the negative ln 2. Now, if you only had e to the ln 2, then the e and the ln would cancel out right away, and your answer would just be 2. Right? You say, what do I do with a negative? To get rid of the negative, you make it climb up as an exponent. So that negative 1 climbs up here, 2 to the negative 1. And now the e and the ln can cancel each other out. Okay, so you just have 2 to the negative 1, which is 1/2. So the final answer is 1/2. Okay, part B. Okay. Somebody is out there is unmuted. Can you please mute yourself? Okay. Everybody please mute. Heard somebody sneezing or whatever. Okay. All right. e to the ln of ln e cubed. Okay, it looks kind of weird, but it's actually easier than you might think. The simple principle here is anytime you have an ln and an e back to back, which is like this, or like this, they cancel each other out. Okay? So you might look at this and say, oh, I don't get it. I'm kind of dizzy. It's dizzying to me with all that. Okay. Well, for order of operations, you're supposed to do what's in parentheses first anyway. Right? So I'll just look at this. ln e cubed. What is ln e cubed? Well, the ln and the e cancel out, so it's just 3. So that part right there is just 3. Okay, so now I'll write it as e to the ln 3. Again, e and ln will cancel out, so you just have 3. Okay, so the answer is simply 3. And by the way, this is not really a calculator problem, but if you tried it on your calculator, if you tried to punch out, let's say, ln e cubed, you would see 3. And likewise, if you tried to hit e to the ln 3, you would also get 3. All right? Okay, 40, we want you to write it as a single log. And so there's some problems that are like that. Expressed as a single logarithm, ln b plus 2 ln c minus 3 ln d. Okay, so there's 3 problems that are like that. I'll do 40 because it's an even one. All right, so just like the previous problem way back here, all the coefficients get to climb up. Okay, now this one doesn't have any coefficients, so don't worry about it. But this 2 gets to climb up there, and that 3 gets to climb up there. So it's going to be c squared and d cubed. So ln b stays the same. Okay, but 2 ln c, the 2 will climb up and become plus ln c squared. And this 3 climbs up, becoming minus ln of d cubed. Remember, ln stands for natural log or log natural. And then you might recall a property of logs that if I have ln of x plus ln of y, it's ln of x times y. You get to multiply them, right? So it's going to be that times that. And then if you have a subtraction, you end up dividing by this. Okay, so now put them all together. Ln b times c squared, so bc squared. And since this one's a minus, that goes on the bottom. So it's over d cubed. Okay, so one more time, we have an addition like this. Ln of x plus ln of y is ln x times y. Okay, but if you have a minus, let's say ln of p minus ln of q, that would be ln of p over q, the quotient. Okay, so plus here means multiply these 2 guys here, bc squared, and the minus means bring that downstairs, d cubed like that. Okay, then 42a, I'll just do a because b is very similar. It just says change the log. Okay, so most of us don't have a calculator button that can do log base 5 or log base 3 or whatever. And the reason for that is we don't need it. We just change the base. Okay, so log base 5 of 10, one of the properties of logs is that I can write it as ln of the top divided by ln of the bottom. So just change it to ln. And it's not really any mystery because when you write it like this, right, the 10 is kind of higher than the 5, right? See how the 10 is higher than the 5? So you just go ln of 10 over ln 5, the one that's above, the one on the bottom, and just punch it in your calculator. Okay, so just punch out on your machine ln 10 divided by ln 5. I'm guessing most of you know how to use your calculator. 1.43, blah, 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 blah. A quick word, and I mentioned this in the video, some of you on your calculators, when you hit ln, it automatically gives you a left paren. Okay, then you folks have to close it with a right paren. Okay, so now my calculator, when I hit ln, it doesn't do that. But some of you, once you hit ln, sorry, it shows up with the left paren. Then you folks have to close it. So if I want ln of 10, I have to hit ln 10, close the parentheses, and then divided by ln. If you get the left paren, then put 5, close parentheses. So now it says ln 10 divided by ln 5. And there is 1.4306, blah, 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 blah. And incidentally, since you get 1.43 and so on, somebody might ask, am I allowed to cancel ln here? Well, if you cancel the ln's, you have 10 over 5. What's 10 over 5? 2. And that's not that. So evidently, no, that's not a law. You can't just cancel ln's. You don't get the same thing. So just work it out. Okay, 47a. Make a rough sketch and use our transformations. Do not use a calculator. Okay, y equals log base 10 of x plus 5. Okay, now logs in general all look like this. Okay, so log base 10 of x looks like that. They all pass through the point 1, 0. And the y-axis is an asymptote. So if I replace x with x plus 5, that's a transformation, right? The graph gets translated 5 units to the left. You go left 5 when you replace it with parentheses x plus 5. So the key point 1, 0, if I go 5 left, that comes out to negative 4, 0. And then I just draw the same type of graph. So this is y equals log base 10 of x plus 5. And the vertical asymptote is over here. Where is here? Well, it used to be the y-axis, which has the equation x equals 0. If I move over, it's going to be x equals 5. Right? So the asymptote is x equals negative 5. That's the asymptote. Okay, so a general log function looks like this. They all pass through 1, 0. And then they told me to go 5 to the left. So I just take the key point 1, 0, move it back to negative 4, 0. Move the asymptote over 5 to the left. So the asymptote used to be the y-axis, which is x equals 0. Move it over here, x equals negative 5. Okay, y equals negative ln x. Okay. Now, if you can temporarily ignore the red, okay, just the blue, y equals ln x looks like this. There's my natural log function. Okay. Side note, do you remember what this key point was? All the log functions go through it. It's 1, 0. Okay, now what happens when you have a negative? Negative reflects across the x-axis, you might recall, right? And easy way to remember that, so I'll take a little time out here with a different sheet of paper. You recall y equals x squared. Y equals x squared. And what happens if I put a negative there? Y equals negative x squared, right? You just reflect across the x-axis. And instead of going up, it'll go down. Okay, so if I replace a function with negative the function, you reflect across the x-axis. Okay, so how do I do that over here? I think the best way to do this, since the graph itself crosses the x-axis, is just split it in parts. Okay, so the actual graph of ln is this. Okay, and if it's hard to see the reflection across the x-axis, just take them in parts. Okay, take just this part here, right? If I only take this part, reflect across the x-axis, you can get this part. Right? So I got that in red. And then separately work on this part. Okay? So if I work on this part, the part that's below the x-axis, right? Reflect that across the x-axis and it comes up to here. Right? So now you have your final answer. Okay, so if you have a graph which crosses the x-axis and you want the reflection, it might be kind of hard to see, maybe split it into pieces, right? Just look only at that. If you look only at that, then maybe you can see, oh yeah, if you reflect, you just have that. And then separately look at this part, and you say to yourself, if I reflect that, put a mirror over here, then you get this part. So now there's the whole thing. So the original graph, the blue one, y equals ln x, and then the red one, that looks like the reflection, y equals negative ln x. Is that okay? Okay, so that's 47. Okay, next one I want to show you was up to something like 52. You have some problems here where you're supposed to solve for x. Okay, so I'll try to show you some of the evens. Looks like there's part A and part B here. So I will do 52, A and B, it looks like. Okay, so the original was e to the ln x squared minus 1 equals 3. Again, ignore the date. Okay, well, I've already given away the answer, but the original said ln blah, blah, blah equals 3. Okay, to get rid of an ln, you exponentiate, you put an e. The way you do it's kind of funny. You have to put the e down and to the left, so I have it in red. Okay, so you're not supposed to put the e right next to it. That would make it look like you're multiplying. But it's almost like the original problem was this, right? Now you kind of come down and sink it to the left. So e goes here. You exponentiate both sides. Some people say you e both sides, but properly you're supposed to say exponentiate. I mean, e is not really a verb, but anyway, exponentiate both sides. Then these cancel out. Okay, then x squared minus 1 equals e cubed. And now that's not that big a deal to solve. So add 1, right? Add 1 and take the square root. So there it is. Add 1, take the square root. Square root requires a plus or minus. So x is plus or minus square root of e cubed plus 1. And that's my answer. So plus or minus radical e cubed plus 1. Leave your answer like that. You don't need to punch it in your calculator. In fact, I want you to be able to show me that you can write that. So no calculator necessary. E is about 2.7, so 2.7 times 2.7 times 2.7 plus 1 square root. But, you know, this is not really a calculator class, so just leave it like that. Okay, part B. E to the 2x minus 3e to the x plus 2 equals 0. Okay, to do this one thing you want to notice is that if you square e to the x, you get e to the 2x. This thing squared is that, which means it's in essence just like y squared minus 3y plus 2 equals 0. It's a factorization game. Y squared minus 3y plus 2 equals 0, you know how to do. This is really the same thing. So when I try to factorize it, I can just put it like this. It's e to the x squared. This is the same as e to the 2x, right? Minus 3 e to the x plus 2 equals 0. So when I factor, I'm just going to pretend it's like y squared minus 3y plus 2 equals 0, right? If it's y squared minus 3y plus 2, you would go parentheses, parentheses, y. So instead of y, it's e to the x, right? And then I see a 3 and a 2. What two numbers have a product of 2 and a sum of 3? Well, 2 and 1. And you know the signs are both negatives. A negative and a plus means they're both minus. So there we go. E to the x minus 1, e to the x minus 2. You can check your answer. Right? Multiply it back out. Let's multiply it back out. FOIL, as it were. What's that times that? E to the x times e to the x is e to the 2x. Got that over here. Minus 2 e to the x minus 1 e to the x. That is minus 3 e to the x. And negative 1 times negative 2 is indeed 2. So it looks like we're good. Okay, so you know by the zero factor property, either this equals 0 or this equals 0. Well, that means e to the x equals 1 or e to the x equals 2. Right? So I have e to the x equals 1 or e to the x equals 2. Take the natural log of both sides. Right? To get rid of an e, do ln. Conversely, to get rid of an ln, you do an e. Okay, so ln. Okay, the natural log of 1 comes out to be 0. And you should put that. X equals 0. ln here, you get ln 2. Just leave it as ln 2. Don't change it to 0.693, whatever. Okay, so my solutions are x equals 0 or x equals the natural log of 2. Okay. All right, 54. ln x equals 1. And this one, e to the whatever, e to the ax equals c, e to the bx. A is not equal to b. We're not sure what that significance is, but we'll see. Okay, ln x equals 1. Too many ln's, but how to get rid of an ln? You put an e. So exponentiate both sides, and the e gets sunken down to the left. So don't put the e over here. Don't put the e over here. It goes down into the left. It's almost like e wants an exponent, right? You want there to be an exponent. So put an e here, an e here. These guys cancel out. E to the first power is just e. So I have ln x equals e now. Right? So ln x equals e. I got rid of this ln. Now I need to get rid of this ln. So how do I get rid of this ln? Same thing. Put another e. Exponentiate, exponentiate. These cancel out. So x is equal to e to the e power. I know that sounds kind of weird, but it's 2.718 raised to the 2.718, whatever that is. You can punch in your calculator. I don't feel like it, but it's something. But yeah, just leave it like that. So you exponentiate twice. You need an e to knock out that one. Then you can have a separate one to knock out that one. So the answer is just e to the e. Okay, then for part B, it said e to the ax equals c e to the bx. A is not equal to b. All right, so how do I do that? So first thing I'm going to do is divide both sides by e to the bx. So if I divide by e to the bx, they cancel out here, and I have this thing, e to the ax over e to the bx. So the right-hand side is just going to be c. C equals e to the ax over e to the bx. Okay. And do you recall what happens when I have something like this? E to the ax over e to the bx. I'm supposed to subtract these two, right? Like if it was e to the 7th over e to the 5th, you would subtract 7 minus 5 is 2, right? So same thing here. That minus that. So now it looks like this. E to the ax minus bx equals c. Okay, so again, I divide both sides by this here, e to the bx. So the right-hand side is c. The left-hand side is e to the, subtract these two, ax minus bx. And now I want to get rid of that e. How do you get rid of the e? ln. Take the natural log of both sides. So that means these cancel out. ln and an e back-to-back cancel out, or e raised to the ln x property, they cancel out. So these cancel out. Ax minus bx equals natural log of c. ln stands for natural log. Factor out the x. A minus b equals natural log of c. Divide both sides by a minus b, and you got it. So x equals natural log of c over a minus b. And that must be the reason why they said a cannot equal to b. Because what happens if a and b are equal? Then you'd be divided by 0, right? So that's why they say a cannot be b. But we didn't know that ahead of time. You don't know that until you actually figure all this stuff out. So final answer, ln c over a minus b. Okay, so that's that. The remainder of the problems are a review of trig. So we got some trig going on now. There's 63, 64, and some more over there. Okay, so how do you do the trig ones now? So 63A, inverse cosine of -1. And by the way, they say some of these should be done without a calculator. Now, you know I'm letting you have a calculator on the exam, so you could just punch this in your calculator and give you the answer. Okay, you can use that as a double check, but I might want you to actually go through the derivation. Okay, show me something, then double check that you did it the right way. So how do you do this? And by the way, when it's like this, it's understood to be in radian mode, unless I say otherwise. Okay, so you should know how to change it. Let's say on this calculator, I have to switch to mode. Okay, so there's radians or degrees. So on my calculator, I hit mode, which was up here. So second function mode. So just check your calculator, radians or degrees. And so let's say I want to change to degrees. I come over here to degree and hit enter. So now I'm degree mode. And I get back to radian, I go back to radian and hit enter, I'm back in radian mode. Okay, or if you have a more rudimentary calculator like this one, then this one, DRG, that stands for degrees, radians, and gradients. So if I just turn on, okay, right now it's in degree mode. So if I hit DRG, whoops, it switches to radian. G stands for gradient. There's actually another unit of measure for angles called the gradient. We won't use it. Okay, so if I hit it again, it's back to degrees. So degrees, radians, don't worry about gradients. If you just got to know what a gradient is, it turns out that 400 gradients is one revolution. So if I go all the way around the circle, that's 360 degrees, or 2 pi radians, or 400 gradients. Okay, but you don't have to write that down. I'm not even going to write it down to confuse you, but that's what the G might stand for. But sometimes it's useful to have something called gradients, but I'm not going to use it. Okay, so how do you do this without a calculator? Well, I would call it theta. So inverse cosine of -1 equals theta. Again, that -1 means inverse. It's not reciprocal. So this does not mean secant. Repeat, this is not the secant function, okay, which is the reciprocal of the cosine. This is a different function. It's called the inverse cosine, okay, which is the inverse function of the cosine. So what you do is write this without the -1. Okay? And you remember when I do the inverse function, you just switch around these two. So this says the same thing as cosine of theta equals -1. Okay? So remember we were doing the inverse functions, right? If inverse cosine of -1 is theta, that means cosine of theta is -1. So for inverse and the function, just switch around the x and y. So inverse cosine of -1 equals theta means cosine theta equals -1. Okay, and then on a unit circle, okay, you want the x coordinate to be -1. X coordinate -1 is way over here in standard position. So where's there? That's 180 degrees or pi radians. Okay, so the answer that we want is pi. And by the way, some calculators give you the pi, but some of them don't. They might say 3.14 or whatever, which is another reason why I don't want you to just rely on the calculator solely. Okay, you should be able to do this trig stuff here. Okay. Part B, inverse sine of 0.5. Inverse sine of 0.5. Okay. Again, without a calculator, how would you do it? So call it theta. Now, write this without the inverse. So give me a statement that just says sine. So if you want the sine, you just switch the 0.5 and the theta around. So you're not taking a sine of 0.5, you're taking a sine of theta. So sine of theta is 0.5 or 1/2. Okay. So on a unit circle, do you recall what nice angle has a sine of 1/2? That's pi over 6, 30 degrees or pi over 6. And one way you can get around that if you forget, is what I sometimes do is draw myself an angle. Okay, sine, that controls the y coordinate. All right, so the y coordinate, I just go up halfway, come across here, and I say, what does that angle look like? It looks like 30 degrees, or pi over 6. Okay, and now, so the answer is pi over 6. You might say, what about way over here, which is 5 pi over 6? After all, the sine of 5 pi over 6 is also 1/2, which is true. But by definition of the inverse sine function, inverse sine, you can only have something between negative pi over 2 and pi over 2. By definition, by the rules of the game. Okay, so maybe I'll sneak that in here. Inverse sine of x returns an angle in the closed interval from negative pi over 2 to pi over 2. Okay, inverse sine, you can only have an angle between negative pi over 2 and pi over 2. Otherwise, you wouldn't have a function. Okay, so you can't say pi over 6 and 5 pi over 6. 5 pi over 6 is not between negative pi over 2 and pi over 2. So we just want here, first quadrant angle, which makes sense. We like the first quadrant. Okay, 65A. Well, this one you definitely cannot do on your calculator because we have no calculator button that does, not only can it not do cosecant, but you can't do inverse cosecant either. Okay, so the original problem was like that, inverse cosecant of radical 2. Okay, so call it theta. Okay, I don't like that. I don't like that, so I get rid of it. How do I get rid of that negative 1? Instead of inverse cosecant, let's just have cosecant. So what cosecant statement can I make? If inverse cosecant of radical 2 equals theta, switch them around. So cosecant of theta equals radical 2. Right? So again, the principle of having the inverse function. If you change a function to its inverse, you just switch these two around. Cosecant of theta equals radical 2. Now I will reciprocate. What is the reciprocal of the cosecant function? Reciprocal of cosecant is sine. By the way, a memory trick again is if one function has a co, the reciprocal does not have a co. So for instance, cosecant, there's a co, right? So the reciprocal does not have a co, that would be sine. On the other hand, what's the reciprocal of cosine? Cosine, there's a co. That means the reciprocal does not have a co, secant. So cosine and secant. And I think most people are good with tangent, cotangent. There's not really any mystery there. Reciprocal of tangent is cotangent. So I flip this and I flip this. If two things are equal, the reciprocals are equal. So I flip this, sine of theta. I reciprocate radical 2. That's 1 over radical 2. And you might recall 1 over radical 2 is the same as radical 2 over 2. Right? If you rationalize the denominator, remember that trick? Multiply top and bottom by radical 2. Okay, this trick that you might recall from algebra. Then this is radical 2 times radical 2, which is 2. So square root of 2 over 2. Hopefully you recognize, oh yeah, radical 2 over 2, 45 degrees, or pi over 4. So the answer is pi over 4 for this one. Okay, 67A is a little bit harder. Inverse cotangent of negative radical 3. Oh boy, that's a lot harder. And notice again, you can't do that on your calculator because we have no button for cotangent or inverse cotangent. So how do you do it? So the original problem says inverse cotangent of negative radical 3. Again, call it theta. Get rid of the negative 1. So the next thing is to give me a statement that doesn't have the negative 1 there, just cotangent. So am I taking the cotangent of negative radical 3? No, I'm not. I'm taking the inverse cotangent of negative radical 3. I must be taking cotangent of something else. There's only one other else, theta. So here we go. Cotangent of theta is negative radical 3, which I can write as negative radical 3 over 1. Okay, now there's a trick to do, so you can follow along what this trick is. I'm writing negative radical 3 over 1. Cotangent is which trig function divided by which other trig function? Do you recall? For cotangent? Cotangent is cosine over sine, right? Now tangent, the reciprocal, tangent was sine over cosine, right? So cotangent is cosine over sine. So cotangent is cosine over sine is negative radical 3 over 1. Okay, now I'm going to do a trick. So how do I get this trick? It works. All right. Divide top and bottom by 2, like this. I know that's a real weird step, but it works. Cosine of theta over sine of theta, negative radical 3 over 1, divide top and bottom by 2. Okay, because now it says cosine of theta is negative radical 3 over 2, sine of theta is equal to 1/2. Okay, well, sine of theta is 1/2. I just did that. That's pi over 6. That's also 5 pi over 6. Okay, this time the cosine comes out to be negative. Okay, so if the cosine is negative, but the sine is positive, that makes me in quadrant 2. So this time I am in quadrant 2, so I do want the second quadrant angle. So the answer is 5 pi over 6. So I want 5 pi over 6 as my answer. All right, then that's pretty much about it. The last thing I'll show you before I stop today is a reminder of right triangle trigonometry. So the problems at the very end require some right triangle trigonometry. I don't have time to do them, but I'll just give you the introduction to right triangle trigonometry. So some of these weird problems at the end, okay, we have to remember what happens with right triangle trig. So let me put this for review from trig. And again, since you're allowed a cheat sheet, you can just put this on your cheat sheet. So if I have a right triangle, and I call this angle theta, let's say. So if I go across it, that's the opposite side. I label that as OPP. So you have the opposite side. This side next to it was the adjacent side, ADJ. And we have the hypotenuse, HYP. Right? I'm not writing the whole thing out because you've heard of this before. Right? So if you have a given theta, angle theta, adjacent, opposite, hypotenuse. And a quick word, you might say, well, isn't this side also the adjacent? Well, this is already called a hypotenuse, right? So I guess a way you can say the adjacent is the side next to the theta, but isn't the hypotenuse. Okay, opposite is pretty straightforward. You just go opposite, OPP, okay? I mean, you could argue at the beginning, well, this could be adjacent, this could also be adjacent. Yes, but this is already the hypotenuse, the longest side. And where's the hypotenuse? It's always opposite the 90-degree angle. So adjacent is not the hypotenuse. So here's the hypotenuse. Okay, and some of you may have heard of Sohcahtoa. If you've never heard of Sohcahtoa, that's okay. So what's Sohcahtoa? It's Sohcahtoa. Okay, so you might recall sine of theta is opposite over hypotenuse, SOH. So the sine of theta is the opposite divided by the hypotenuse, which is what so means, SOH. CAH means cosine of theta is adjacent over the hypotenuse. So if you have a right triangle and you want the cosine of this angle, you take the adjacent side divided by the hypotenuse. And finally, TOA, TOA, tangent theta is opposite over adjacent. So you have a given angle, the tangent was the opposite divided by the adjacent side. Okay, and so I just wanted to share that with you before we do this, but you've heard of that before, so I want to just give that to you before the end of the day. Okay. All right, so that'll do it for today, folks. I'm going to stop the share, and that is that. All right, so let's see. We only have about 5 minutes left. Let me check the chat. Okay, so again, if you think I missed you on the, attendance, then just send me an email later. Let's see, do that. Okay, where's chat here. Okay, 54, 67. Okay, let me see. Get back to sharing the screen. Whoops. Okay, somebody wanted 67 again. So here was 67. I'll hold it for maybe 15 seconds. So either do a screenshot, or if you don't know how to do that, get your cell phone out maybe and take a picture of this for 67. Okay. And let's see, I forgot what somebody else wanted. 54. Okay, so you want to see 54 again, maybe? Okay, well, there are two parts to it. I'm guessing whoever asked you wanted B. A was easy, just E to knock out this ln, do another E to knock out this ln. Okay, so the original was ln, ln. To get rid of this ln, you do an E. These are gone. And to get rid of this E, you do another E. To get rid of this ln, you do another E. So the answer is E to the E. Okay, maybe you wanted B again. So quickly for this one, e to the ax equals c e to the bx. First, you divide both sides by e to the bx. I want all the x's on the same side. So divide by e to the bx. These cancel out. So the right-hand side is c. The left side is e to the ax over e to the bx, which is e to the ax minus bx, right? Because you take that minus that, right? You subtract the exponents. Okay, now to get rid of this e, you ln both sides. So ln, ln. These guys cancel out. So I have ax minus bx equals natural log of c. Factor out the x. Whoops. Factor out the x. And just divide by a minus b. So x equals ln c over a minus b. Like that. Okay. And let's see. I think that's it for the chat. Time is it? It's almost time anyway. Anybody else have something real quick? No? Okay, I think that'll do it then. All right, folks. So have a good afternoon. I'll see you tomorrow then. Everybody have a good day. So tomorrow I'll try to finish it up, and maybe I'll get started even with the next chapter. But maybe I'll let you ask questions. Thursday, question and answer, and Friday's a test. All right, that's it, folks. Bye.
Thank you, Professor.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.